And we're back. Welcome back from the weekend. Today we'll continue on with our discussion from Chapter 2 material in the main text, namely OS structures. Before we begin, some administrative bits. The reading by the 17th from the text is pages 55 through 74. Please make sure you're keeping up with the reading. In addition, the reading by the 24th of September, these two pieces are on Blackboard. It's a link to a YouTube video, C Programming Essentials in 4 hours, and also a C Programming tutorial. That tutorial is meant or intended as a reference for the things you will see in that tutorial. Now, these aren't the tutorial video. These are not the only C tutorials and information and references out there. You're free to use whatever resonates with you, but the material in the YouTube video and the supporting reference in the tutorial, I will hold you responsible for. Okay, we will have an upcoming project assignment that will require you to use C. So please make sure you are not just sitting idly by. Please make sure you are actively engaging with the material at least 1 hour a day. Okay, so where we last left off, we took a look at operating system services, and we spoke about the services that are made available generally within the operating system, such as the hardware abstraction layer. And that hardware abstraction layer presented a generalized interface for use by the operating system for interacting with various hardware devices. Now, generally in this diagram, those interfaces for services are typically at the seams between major components in your system. And so we have the HAL layer between the operating system and the hardware. We have the runtime services in between the operating system and the system calls. We have the system calls, which is that seam, if you will, that presents the underlying runtime services to the programs above. Now, certainly some of those programs are system programs like the user interface, be that command line, batch, or GUI. And then we also have other programs such as Microsoft Word or Dropbox, which would run on top of all of this. All right. We also talked about touchscreen interfaces, and the thing where interfaces are going when we mentioned this originally was that interfaces are really looking at sensors, so touchscreen, if you will. The screen has touch-sensitive material, a sensor, and people have implemented gestures for interacting with the various parts of your system and the application. In addition, voice interfaces are getting increasingly popular. Apple's Siri product and Amazon's iOS, as well as Google's Nest Hub products are very, very popular, Google Voice Assistant. So let's continue on and let's look at system calls. System calls are the programmatic interface that you use to access these runtime services provided by the operating system. And these system calls are functions or libraries of functions, and they're written in a high-level language, C, C++, Java, Python. They all have system calls, and this is your entry point, you being the program, for making use of the collection of runtime services for doing things like reading and writing a file, sending data out the network, reading data from the network inbound to the machine, etc. And so these are mostly interfaces, and these APIs, application program interfaces, those are the libraries of functions that I alluded to. And this is the entry point that an application uses effectively to instruct the operating system, hey, go ahead and do something on my behalf. Now, the system calls names used throughout this particular text, the operating system's concept, are fairly generic. There's a standard in Unix called POSIX, Portable Operating System Interface, that is used to give a standardized set of function signatures, if you will, to make it consistent for when you're writing applications to use system calls across various Unixes. So the three most common APIs for system calls are Win32 for Windows, POSIX for Linux-based systems, and Java has them, Java API, Java system calls. Python has them as well. So an example of a system call, imagine, if you will, you tried to copy some file in .txt, and you issued the copy command, CP, and you gave it in.txt, the source file it's going to copy from, and out.txt, the destination file. So you want to make a copy of the contents of in.txt, and that copy is going to be called a new file name called out.txt. So thinking about what happens when you copy a file, you're continually reading from the source file, in.txt in this case, and you're sending that what you're reading, that text, that data, to that other file. So thinking about what happens underneath the covers, you have a stream of sectors in tracks on different platters on your disk associated with the input file. You're reading each one of these, although that byte information in each sector strung together as a linked list laid out on disk. And you're taking each one, you're writing it to a new sequence or byte stream associated with that other file. So the example given in the book, this sequence of system calls, the first thing you do as the system call implementation that implements the copy command, acquires the file name, it writes something to the screen so that you'll know what it's doing. It says, hey, give me this file name. You type it in. It accepts your input. Then it asks for the output file name. Okay, you give it the output file name, writes a prompt to the screen. You type it in. It accepts the input. So then this copy program enterprises to open the input file. And if there's no input file, then it says, all right, stop. Something is dramatically wrong. It does not exist. It then creates the output file, and if the file already exists, stop, because there's something wrong. Because you're going to open a new file or create a new file, it can't already exist in general. But there are exceptions to this, and I'll talk a little bit about that another time. So then you're going to continually read a little bit, a few sectors worth of data from the input file, and then write a few sectors worth of data to the output file. And then you keep doing this again and again and again, alternating between reading from input and writing to output. And you keep doing that until the read fails. And the reason why you do that until the read fails is that once the read fails, it means that there's nothing left to read and you're done. So as a response to this failure condition, there's nothing else to read, no more sectors in some stream of bytes to read. You close the output file, and then you notify the user with a message to the screen that you have terminated, you're done reading, and then you exit normally. And so all of this happens as a series of operations, and these operations are implemented in the file system runtime services that the operating system makes use of. But from the perspective of the application that wants to perform this copy operation, it's just a single system call. So that implementation of what it means to copy the contents of one input stream to another input stream on disk is implemented, those details implemented in the system call that the operating system makes use of. And moreover, the operating system performs these activities on behalf of the user program. And so this is an example of the read API call. And in the Unix operating systems, and Apple's Mac OS is a variant of Unix, so-called BSD Unix, Berkeley Systems Division. And the manual pages are a set of API guides that tell you what the various functions do. And so here you see this command, man read. I'll circle it. Let me set my pen here. And I will choose blue. I think that works for us today. Man read, when you call this man function at a command line, it says run the manual pages, so it will look up that entry for the read system call. And it gives you something that typically looks like this. And in this description, it'll tell you what header file, that's the header file, what header file is used to define the library. So what collection of functions, so library or collection of functions, do I look to in order to find this read function? And so every function has a function name, that's read. That hasn't changed. It also has a return value. What is the specific type, data type, the layout of the data and its type that this function will return to you when it is called. Then it also has a comma-separated list of parameters. These are the payload, if you will, payload that this function needs in order to run. And so when the operating system is calling the runtime functions that implement this particular systems call on behalf of the calling application, the payload is what is given to the operating system. So if you were going to write a file, well, you give it the data that's going to write. If you're going to read a file, you have to give it that location in memory where the contents of the file that's read are stored, right? Where in memory should I place what I'm reading? And so in this case, for the read, you have something called a file descriptor, which is your way for identifying which file. And you notice this is an integer. The system doesn't care about actual text names. Text names are only there for our human benefit, not the operating system's benefit. And in fact, if you were to look into the implementation of a Linux kernel, you'd see that this file descriptor is an integer, and it's an integer because it literally is the index into a list where you find records corresponding to the file block pointer information. And so here we have the payload void star buff, which is the memory address where the result of this read will be stored, and then size t count, that's the number of bytes that should be read. So you tell it which file to read, where to store, and how much to read. Okay, and then the man file or manual pages also contain a description of what that function does. And this is fairly standard on Unixes. And so let's take a look at the system call implementation. I alluded to earlier how the operating system calls the runtime services in the implementation of what it means to perform that particular system call. And typically for every system call, and they're numbered, you have an integer. And this integer is unique for the system call. And when the application calls the system call, the operating system receives internally a number that says which particular system call implementation should I perform. And so the system call interface then maintains a table, and that table is indexed using that system call number in order to execute the correct set of system services and runtime services. And so this system call interface invokes the intended system call in the operating system kernel, and the operating system kernel, after it completes this set of actions for the system call implementation, returns back the status of the call. All right, that status indicates the success or failure of that system call, but it also returns back any return values should they need to be returned back to the calling application. And so the caller, in this case, knows nothing about how the system call is implemented. All it knows is that as long as it pays attention to and follows what that parameter types, what the parameter types are, and what the behaviors of the function are and the return types, then it can use it. But it has no understanding of the application of the implementation of the system call. And this is on purpose. It's a form of protection. It enforces this idea of an interface, but does not give the application access to what those behaviors are that the kernel engages in. And so most of the details of the operating system's interface is hidden from the programmer, right? That's part of the API for how system calls are presented. And it's managed by runtime libraries that collectively are these system services, system runtimes that we talked about in the previous module. And so here's an example. You have your user application running on top. You might call open from the system call libraries. You have your switch to kernel mode from user mode. That's your protection mechanism. And then you index into system call table. It indexes the correct system call as an entry in that table. It knows where to execute that code set of system services. It goes ahead and runs the implementation of what it means to open the details of that system call. It then returns, and it gives the return status in addition to returning whatever parameters were agreed upon through the specification of the system call, that particular system call interface. And so oftentimes, as I alluded to before with that read, you have a number of parameters, more information that is simply just calling the system call, i.e. the system call number. And so the exact type of the information that's needed in order to execute that system call can differ. And so, for example, in a read a file system call, you need, as I said before, which particular file you're going to read, where you're going to store that information in memory, and the amount of data, the number of bytes to read. If it were a write, you need to know which file to write. You also need to know what information you're going to write, and you also need to know other things like whether you're going to overwrite and things like that. And so there are different methods that are used to pass parameters from the application to the kernel. And the reason why that's needed is exactly for protection reasons. And so if the user application doesn't have direct access to the system call implementation, there has to be some way to transfer generic data from the application into the kernel, that data that's needed in order to execute that system call. And so the simplest method is to use registers. We said registers in the CPU are used to store temporary information. And that's good, but sometimes there can be more parameters than there are registers. You can imagine if you only have 16 registers in your CPU and you need 32 different pieces of information for your parameters, it's not going to fit. Another way to do that is to store parameters in a block or table in memory. And in that case, all you specify to the kernel is a memory address associated with that block of information. And that memory address is then passed in a register on the CPU, and the system call implementation, the operating system kernel, then loads that memory address from that register in the CPU, and then it accesses the memory location whose value or whose address was stored in the register. This is the approach taken by Linux and also Solaris. Solaris is the Unix operating system created by Sun Microsystems, which was acquired by Oracle Corporation when the dot-com bust happened in the early 2000s. And so another approach is parameters can be pushed onto a system stack. Remember, we talked about the stack pointer a little bit in previous module. So these parameters can be pushed on the stack by the application and subsequently popped off the stack by the operating system kernel prior to execution of the details of that system call implementation. And so these ideas of using blocks and stacks place no limitation on the number of parameters that you need to pass from the application to the operating system runtime, because it's as many parameters as you can store in memory effectively. And the stack is carved out of memory as well. Okay, so here's an example of using registers to pass parameters. And so you have a user program. You're going to call a system call, and that system call number inside of the system call API function happens to have a system call number of 13. You have load an address, and you put in the registers the parameters that you're going to store in your memory, in your registers on the CPU. So then you have an identifier that tells the system which register those parameters can be found in. And that's all sent to the operating system as part of that system call. And so the operating system looks up entry 13 in that system call table, and it grabs the parameters that were stored in that register identifiable by some address, and then it executes the code for system call 13. What are some of the types of system calls? Well, we have things for processes, the creation and termination of a process, the abnormal exiting or aborting of a process. You can load a program or execute it. So that loading means to take that file for the program off disk and to create a structure and memory for the runtime representation of a process, and then to have it scheduled to be executed on the CPU. You can wait for some amount of time, allocate free memory, dump memory. You can lock resources so that you can have the orderly access to limited resources by multiple executing programs. File management, as we said, the file management system presents the illusion of a contiguous tape of bytes, but underneath the cover, it's a linked list of sectors that happen to be laid out on the disk in various platters and tracks. And so you can open and close a file, create, delete a file, you can read or write, you can shift the file around, repositioning it on disk, and you can also set attributes that govern who can access files and what they can do with those files. You can also do device management. You can read or write to devices. You can get attachments or channels of communication, create them with devices. You can read information from them or send information to them, the read and the write. Information maintenance. So you can look at things like date and time. You can look at system data and other attributes associated with different processes or files. You can send and receive data, your communication, both on your machine or off on the network to a process on another machine. There are different ways of doing communications. You can transfer between processes on the same machine using shared memory. You can do this between devices, including the network device when you want data to go outbound or inbound from off the machine or coming onto the machine. You can also set protection mechanisms in order to gain access to resources or enforce permissions for things that you want to allow or disallow in terms of interactions of others on various files or other devices on your system. And so these are some examples of system calls in the Windows ecosystem and the Unix ecosystem. So in Windows, it's on this second column, and we see it's a little bit more wordy in its definition. Create process to create process, exit process to exit process, and I won't read all of these off. In Unix, to create a process is called fork command, and to exit a process is called exit. And so these are all over the internet, all over the reference material. So I encourage you to Google search these. There are lots and lots of resources readily available to explain these things to you in very, very great detail. And so an example from the standard C library is the so-called printf command. And what the printf command does is you give it a string in string literal in quotes, and it will send that out to your screen to the console. It's a library call, and this library call calls write, and this particular write will send it to the I/O device for your screen, for your monitor, the terminal, command line interface. And so here we have a C program, and this is just to kind of also introduce you to the various parts of a C program. And so in a C program, we have these routines called, these directives called preprocessor directives. Number sign is how you designate a preprocessor directive, and I'll get more into preprocessors to processing directives towards the end of this module. But this particular number sign include, it says I want to include or pull into my program that I've written the text of whatever this stdio.h file is. Now this is a so-called header file, and what a header file does is it includes the definition or declaration of a function and or types. And so what is a function? It's a statement that says what a function's called, what a function's parameters are that it takes, and what a function returns. Without this header file, none of the function calls in this program would make sense when you tried to compile this program to make use of it as an executable. And so what this header file does, it says, I want to pull in a library of routines, and that library of routines is in this text file called stdio.h. Now, stdio happens to be standard IO, or input-output. And so that is the library of functions, your API, that allows you in C to do IO operations. And so this printing to the screen, it is an IO operation. It takes this string literal and sends it out to the screen device driver and IO controller, and you see it on your console. And so we also have in C, it's so-called block structured, and these block definitions are explicit, delimited by the open curly brace, which is here, and the closed curly brace. Everything in between is a line of the program. Now here we have the printf statement. It is a system call, so it's a function from stdio.h, standard IO, and it is terminated with a semicolon. Again, from the previous module, all C programs are terminated with a semicolon. Now, at the end of this main routine, and this main routine is the main entry point for every program in C, it has a return statement. Now, this return is an integer, which is consistent with that declaration of the main. It returns an integer, takes no parameters or void parameters, and it's called main. And so when you return 0, consequently, that means that there is no error with your program. If you return something that's non-zero, that means your program had an error. So you call printf, and the printf routine calls the API library runtime made available by the C standard library. You switch to kernel mode using a trap. You look up in the table for this runtime implementation of the printf. It goes ahead, calls the write system call. That goes to your console. It returns back. The interrupt returns back to user mode, and now you return back to the program. And so this is an example of the process, or at least the relationship, when you call a system call, and this particular system call is for the printf library call made available by the standard IO library in C. And so when you have a program running, there's a relationship between the operating system and memory and your program. And so in the early days of computing, in the 80s, MS-DOS was king, and that was the predominant operating system. It wasn't really an operating system, but you want to call it an operating environment. It was the predominant operating system of the time. Now, it was very, very simple. You could only run a single program at a time. And so when you ran MS-DOS, you got a command line interface, and you type into this command line interface the name of the program you wanted to run. And so you ran the whole program. You had a single memory space, and what would happen is you'd load the program to memory, overriding everything but the kernel, which stayed in one region of memory. And so here in this schematic, we have free memory, we have the command line interpreter running, and at the bottom of memory, we have the kernel. And so you run your program, the program or process would load in memory, overriding the command line interpreter. And then once your program exited, the kernel would reload the command line interpreter so that you would be presented back with the command line so that you could run your next program. And so it required the kernel to reload the shell, the command line interpreter, so that you could get the next command that you wanted the system to execute, and the command corresponded to an application. So then multitasking came along, and FreeBSD is a free version of Berkeley Systems Division Unix, and you had a login for each user, so it was multi-user, and it was also multitasking. And so the shell would run, and the kernel was also resident in memory, and the command line interpreter would also be resident in memory. And so you start out, when you execute or type in the name of a program to execute, the fork system call would get run. And as a result of fork, the command line interpreter would create a copy of itself. And one of the copies of the command line interpreter would continue to run. And in the other copy, it would call the exec system call. And the exec system call would load that new program off disk to overwrite one of those copies of the command line interpreter that you got when the fork system call completed. And so the shell, or the command line interpreter, that did not get overwritten by the program running would wait for that process to exit and then tear down the resources as necessary. So let's take a look at the system services. System services are programs that make it convenient for this runtime for program development and execution. And you can divide your system services based on, you could kind of go along the lines of the parts of your system that it allows you to modify. So we have file manipulation as a system service, status, so what's happening with parts of your system, kind of like an accounting and reporting mechanism, programming language support, things that programming languages might need in order to access certain parts of the system, program loading and execution, communications, the ability to run things in the background, certain services like printing. If you want to send something to the printer, you have to have some program running that accepts data for the printer and then sends it to the printer. That would run in the background. Things like the maintenance of your file system, and as well as application programs. And so most users, when you think about an operating system, you don't think about the kernel. You typically view the operating system as the collection of system programs and not the actual system calls themselves. And so these system services provide an environment that make it easier and more convenient to write programs, software development. And some of them are user interfaces, others might be more complex. Things like file management allow you to create, delete, copy, rename files at the level of this abstraction presented, which is just a stream of bytes, rather than you having to deal with the individual linked list of sectors that are laid out on disk in the tracks on the platters. There's also status information for reporting for things like date and time, other things having to do with debugging and tracing stuff in the program execution. And some implements things like a registry. Now, Windows has a registry, and that's where you store persistently configuration information for various applications. And some system services will allow you to print output to the terminal, general terminal services as they're called. You also have the ability to modify files, things like text editors that allow you to manipulate files. You have special commands that allow you to search. So you enter in a regular expression, and it's a generic system service allowing you to query within files for the occurrence of certain text that you might desire, as well as certain language support, like things like compilers to allow you to write programs, debuggers that allow you to find errors in programs through your development process. You also have program loading and execution system services, different types of loaders. Some loaders load your program into memory in a specific location and it doesn't move. Others are so-called relocatable loaders. They work based on relative location for items, and they can move them around in memory, the pieces of your program. Other system services are offered for things like creating connections among processes, so you can send and receive data between processes that cooperate in some application, and these processes can be on a single machine. Sometimes they can be on different machines scattered around the network. And so some of these communications deal with individual streams of bytes, others on a message level granularity. So you're talking about messages and not just individual bytes. You also have background services, and these are launched at boot time when you first power up your system. And they do all sorts of system integrity types of operations, things like error logging, things like checking the status of your disk. Because the disk is a mechanical device and the mechanical device can break, it's very important to have a program or service that's always looking at various parts of your disk to make sure that it is healthy and running without errors and no corruption or places on your disk that are bad and cannot store data any longer. You also have system services for application programs. These are run by your users, and they're not generally part of the operating system. You can launch these on the command line, things like mouse clicking programs to read status of what's going on with your mouse pointing device. Let's move on to how you craft these programs, and the focus here is going to be on the C programming language. And so we said that C is a so-called strongly typed language. It's block structured, but it's also a compiled language. You start out with your main program, and that's just a text file, main.c. You run that through your compiler, and your compiler's job is to translate your text statements for your correct C program into assembly language bytecode sequence of ones and zeros that your processor, your CPU, understands. That sequence of bytes, ones and zeros, corresponding to the translated version of your C program, that's called an object file. And now that object file uses other parts of the system, those API calls, those system calls that I talked about. Well, those system calls, they were also compiled, but they're made available as part of the operating system. And so when you have the object file for your program that you have written, that's main.o, you need to now take that main program and paste it together, that object file, with the definitions of ones and zeros for all the system calls you use. And so that pasting together of your main routine with, say, the printf object file, the pasting together is done by something called a linker. And so that linker, its job is to paste together all of the object files, both your program object files and all of the supporting system call implementation object files, to make one big executable. And that's the linker's job to do that. Now, this particular example is called GCC, the GNU Compiler Collection. And GCC is available for free, and it ships with most Linuxes. And so This object file, this is collected together for all the system calls along with the object file as a result of compiling. And it's all pasted together and creates your executable. That's this main output. So here you're saying GCC-C says compile, which file? main.c. It generates the object file, main.o, and now you say GCC-O, so it's going to link, call the output executable main. The object file for the program you're going to use is .o, but here this -lm says paste together the library called libm.o, right? And this libm.o comes in two forms. One is called a dynamic link library, and one is called a shared object on Linux. So DLL is on Windows, and shared object is on Linux. Okay, and so now once you get your pasted together object files, there are two sources. One is from your system call implementation, and the other is from your source code that you write that pasted together to form an executable file. That's main. So now you take your executable and you go to run it. That's where at the command line interface, you type the name of your program and you hit enter. Well, what happens? Well, this executable gets loaded from disk into memory, and the part of the system that does this is the loader. Now this loader, it's responsible for taking the bits and bytes of your program from disk and putting it into system memory, and then it starts the execution at the main function. So that's why Java Object has a main method. That's why Python has a main function, and C also has a main function. That loader's job is to get that program into memory and to start execution at that function called main. So now once that loader loads it, it also needs to load other parts of the system runtime libraries, and these things are the so-called dynamically linked libraries. These dynamically linked libraries, there's some libraries that are loaded only when you try to access functions in that library from the system calls, and there are other libraries that are pasted in at the beginning. That's called static libraries. And so what the static libraries do, they paste in all of the object code for the system call libraries that are needed and called by your function, by your program. What the dynamic one says is I'm going to defer that loading until the point where I actually need to access it, which can be memory saving. Okay. So static linking pastes together the library of routines with a compiled object, which is your source code that you compiled into a single program, your so-called object file. For dynamic linking and loading, then when you paste together your program with the system call object, it's just the name of the system library that is pasted in, and not the actual library contents itself. And when the program is actually run, it consults this name, says, aha, I need to load the standard library, standard IO library. So it looks for the shared object file and it loads it when it needs to run the program. On Linux, it's a .so file, which stands for shared object. And on Windows, it's a dynamic link library, or a so-called DLL file. Okay, so let's segue to Linux interface, and we'll actually go through a really, really quick example with a C program. Okay, so this is a virtual machine environment, and this virtual machine is running Ubuntu Linux version 16.04 long-term support. So I'm going to log in to this, and you'll see I have a graphical desktop. And on this graphical desktop, I have placed a single terminal, and this terminal presents a command line interface that I'm going to use to write an example program. So let me resize this terminal, move that down a little bit. It's a little bit slow. Oops. Okay. So let me select my terminal, and I'm going to go to the preferences, and let me see if I can manipulate the size of this terminal view. Zoom in. Okay. View. Let me zoom in a little more. Control plus plus. Control plus plus. There we go. All right. So let me clear the screen, and I'm going to start out and look at a demo program that I've already written. So I have my demo.c. So let me look at the demo.c. And VI is a terminal editor. So here at the top, I am including a number of libraries that I'm going to use in my program. So I'm going to use standard IO, which is for printing things to the console. I'm going to use standard libraries, stdlib.h. I'm going to include string.h and stddef, standard definition for things like null. And so these number sign includes are so-called preprocessor commands. And what these preprocessor commands do is it is run during the compilation of a program, and it basically pastes in a piece of text defined by the thing that follows in this particular case. So when I say number sign include stdio, I'm saying look on the file system, search for standard.io.h, that file, and take the text of that header file and paste it into this program. And that's happened as a preprocessor. It's processing that happens prior to or pre-compilation. And so number sign include is a so-called preprocessor directive, and it gets the compiler to do things before it actually performs a compilation, where the compilation is a translation of the program from your programming language to the bytecode or the ones and zeros, the bits that have meaning on the CPU. And so I include 4 different library header definitions for various sets of function definitions, or declarations rather, for various types of functions that I'm going to use. This number sign define, that's another preprocessor directive, and what it does is it replaces all occurrences of num_vals, and I just chose that name, with the number 10. And so this is a way of making your code easier to read. Number sign define is the preprocessor directive, and literally it says number sign define space some name space some value. And so every occurrence of num_vals in my program during the compilation or prior to compilation is going to be replaced with the number 10. And that's just a readability thing for the human that's writing the program. And so here I've defined my main routine, and the main routine is required by the C program loader. And this main routine returns an integer. So there's my int type. There's the name of my function, main, open close paren, and I have a comma separated list of the number of parameters to main. Now, argc is the argument count, and that's a requirement of main. And then the second one is char ** argv. So we just said that there's this type called a pointer. And what this particular type is, when I say star, that's pointer to, but it's pointer to char. And so a char * is the same thing as saying a string. So essentially, when I say pointer to star, reading from right to left, argv is the name of the variable, that's the argument, and that's going to be a pointer to strings. And so this char * is a way of saying an array of strings, and we'll talk about that in more detail in another setting. And so inside of this main routine, you'll notice also I define the open close curly brace. Here's the open curly brace up above. Here's the close curly brace down below. This variable is an unsigned char, or uchar. I alluded to it in the previous module. And so it's an 8-bit number that's unsigned, so it's an integer from 0 to 255. So I say create a variable called val pointer, and it's going to be a pointer, that star notation, to an unsigned char. And so here I'm saying this particular variable is a pointer type, and it's going to point or store the memory location where I can find an 8-bit unsigned quantity. And so I'm setting that to null, which is the same way of setting your pointers to 0, if you will, in the beginning. Now, one of the things that languages like Java does for you is when you define variables, the Java runtime actually zeroes things out for you. All references are set to null, and all values are set to 0. And so that's not what C does for you. With C, you explicitly have to initialize your memory all to 0 or your pointers all to null. Otherwise, what will happen is this pointer will assume a value of whatever happened to be in memory when it allocated a space for this val pointer variable. And so we start out, come down here, we print hello world, and that's a system call. It's going to trap to the kernel, and it's going to execute that routine for printing. It's going to write to the console. And so this next command here, I'm allocating memory. This malloc stands for memory allocate, open, close paren, and inside of it, I tell it how much memory in byte count it's going to allocate. So I say size of, however big an unsigned character is, times the number of those unsigned characters I want. So I say 10 many times, allocate something memory that can hold 10 of these, 10 many times, allocate memory that can store this unsigned char, right? So that's the semantics of a malloc in C. You explicitly have to tell it how much memory to allocate. And you notice I terminate that line with a semicolon. That's the standard in C. So when this malloc returns, it's going to return back a pointer that will allow you to access this memory of size unsigned char times 10 num vals. And now you have to do what's called casting, because when you allocate memory, it's a pointer to any type. But in order to be able to use it, you have to tell the C runtime specifically how it should interpret that memory. And this cast operator, open close paren, has an unsigned char star. So it says, take that pointer to the nothing type and convert it to pointer to unsigned char. So that means whatever it's going to access in the memory location, it's going to treat it like unsigned 8-bit quantities. Okay, and so I take that result and I store it in val pointer, and so now I'm ready to go. And so essentially now, after I allocate that memory, again, C requires you to initialize your memory. And so here, this memset, it's a system call, and it says go ahead and you set a piece of memory to a certain value, every byte in that value. How many bytes? That's what this last parameter does, size of unsigned char times num vals. So num vals are 10 times many bytes times the size of an unsigned char. That's how much memory I want to set. Set to what value? Set to 0. That's what that second parameter is. And likewise, starting in what memory location? Whatever memory location happened to have been stored in val pointer. So what this memset does is it sets the memory starting at location stored in pointer variable val pointer. It's going to set it all to zeros, and the number of bytes it's going to set to all zeros is going to be the size of an unsigned char times 10 num vals. So now I loop through each one of those locations starting at val pointer, and I print out its value, right? So I say what's the value in the 0th position, and the 1st position, the 2nd position, the 3rd position, up through and including the 9th position for a total of 10 positions. Now, it just so happens when you have a pointer variable, you can treat it like an array and use the array angle bracket index in order to access those locations. You could also do it directly by just adding to that pointer, but it's a little bit cleaner sometimes to use this array index notation. And so if you say val pointer array index 0, it's going to access what's the 1st position in that memory location, index 1, the next position in that memory location, index 2, and so forth. So here I have a loop for, you give it the int I, all types are declared equals 0, that's the loop index, less than num vals I++. So it goes through and iterates, and each time on that iteration it says the value for the dth position, that's an integer, is whatever is there. So here I print out which position. It's the index starting at 0. I add 1 because I like to say the 1st position, the 2nd position instead of the 0th position, 1st position. And then I print out this what is located in that particular position in that piece of memory that I access with the val pointer variable. So now at the end, I free what's at val pointer. And when you say free, you're saying go ahead and release what I have allocated back to the available free store so someone else can make use of this memory. If you don't, your program will continue to allocate memory that no one else can use, and that's called a memory leak. Okay, so we're going to try this out first with as it is. So I'm going to say gcc compile demo.c. So when I compile demo.c, it creates a demo.o object file, and I had done this before. So let me remove demo, and let me, yes, remove it. Let me remove demo.o, yes. So if I list all the files in that directory, I have demo.c. Now, if you look on the left-hand side, these are the permissions for this file, and we'll talk about that in another sitting. Actually, I did talk about it in the first module, the previous module. If I say gcc-c compile demo.c, I produce the object file, and that object file is demo.o. So now I'm going to link it. That's running the compiler. So if I say link it, I say gcc, all right, that's the GNU compiler collection, -o. The output is going to be called demo, right? That's the object executable file. And the thing I want to link in with it, demo.o, and there we go. So I do that. If I do another listing, I notice that there's an executable now called demo. So if I run demo, we'll see what happens. You'll notice the values at each location of memory stored at val pointer is now zeros. So let's see what happens if I edit this program again and I do not initialize to 0, just to kind of show you why we do this in C. And so here I do the memset to initialize a certain number of bytes starting at val pointer. I initialize that to all zeros. So I'm going to remove that initialization, and I'm going to print out the values that happen to be at that location after I allocate it, because what's going to be there is just what happened to be in that region of memory before it was allocated. So let me rerun GCC to recompile my program, and let me relink that program. And I'm just using up arrow here to scroll through the previous commands. And now I'm going to run demo. And if everything worked out, you'll notice, oh, it's still zeros. I got lucky. All right. And so this wasn't what I was totally expecting, but it's a fortunate situation that occurred. But you have to assume that the memory that you allocate is not always initialized, and it's really, really important to make sure you initialize it. So let's try one experiment. What we're going to do then is we're going to go ahead and we're going to set in another loop. We're going to set, so let me make another loop, and we'll do a before and after type experiment. So now what we're going to do, we start out initialized to all zeros, and now we're going to say val pointer, the ith value, we're going to set it equal to, let's set it equal to the index plus 1, right? So the ith position of memory referenced or beginning at what is described as address in val pointer variable. We're going to set that equal to, let's say, I plus 1, index plus 1. So now after we do that, we're going to print out again the contents of that val pointer. So we start out, we initialize to 0 through the memset. Let's comment that back into the program. Oops. Okay, so we comment that back into the program, and then we loop. In our first loop, we're going to print out the contents, and in our second loop, we're going to set the contents to some non-zero value, and then in the third loop, we're going to print out the contents of that memory once again. And so on the first printout, we'll see the values are all zeros. The second printout, we should see the values are non-zero. And so let's compile here, GCC compile, okay, and let's link. That's the link. let's go ahead and run this program. And we'll notice here, hello world, okay, we did the mem set to all zeros. We printed out the contents, it's all zeros. And then we print it out again, and you'll notice it has actual values. And so we've actually used that pointer to modify the contents of memory. All right, so with that, let me exit this virtual machine and go back into the PowerPoint. Okay, we are back in the PowerPoint, and that concludes our discussion on linker and loader. I showed you linking and loading at the command line in Ubuntu Linux, and showed you use of a pointer and how you can use that pointer variable to set and read contents of memory. So with that, we'll end there. Please make sure you're keeping up with the reading. An assignment will be released that will require you to program in C. You will have ample time with which to complete that assignment, but you have to make sure you are engaging with the material at least 1 hour per day. So with that, as always, please stay healthy, stay safe, and I will see you on Thursday.